Welcome to Signals and Systems Simplified, your complete guide to one of the most fundamental subjects in electronics and communication engineering. Whether you are a second year student trying to grasp the basics or an aspiring engineer preparing to compete in the competitive exams, this series is designed to make signals and systems crystal clear, concept by concept, with examples, intuition, and visualization. We will explore how signals carry information, how systems process them, and why tools like Fourier Transform, Laplace Transform, and Convolution are at the heart of the modern technology, from communication systems to signal processing, AI, and beyond. I am Dr. Sandeep, and through this series, we will break complex theories into simple ideas that you can see, understand, and apply. So hit the subscribe and grab your notebook, and let's start mastering the language that every electronic engineer must know: signals and systems, where we break down the toughest easy concept into easy to understand lessons. Stay tuned as we uncover how signals shape the world of modern engineering. Welcome to this session on Signals and Systems Simplified. These are the concepts every engineer must master. So in this series, we look into 5 major aspects divided into 5 units. In the first unit, let's check what the signal is, analyze the signal, try to understand the analogy between the vectors and signals, what are orthogonal signals and what is orthogonal signal space, and how the signals can be approximated using this orthogonal signal space. Then when we try to compare signals, then we need to understand what is difference between them. That's what we call error. So how do we compare two signals? For comparing two signals, we do use something called error, and here the mean square error comes to our rescue, and we just try to see what mean square error is, how that is useful for our day-to-day activities, and look at what are orthogonal sets of signals are there and how that can be used to represent any signal in the signal space. Then we try to classify the signals and the systems in using different tools, different yardsticks, and then try to see some standard examples of the signals like exponential, sinusoidal, impulse, step, and signum functions. So we do use these standard signals to represent a signal and try to understand the system behavior. So if we can understand a system's behavior through one of these standard signals, then we can understand what exactly the system is, and we have two purposes here. One, to understand for a given system, if a particular signal is passed through, what comes out. So we know the input, we know the system, we want to know what the output will be. So this is what we call analysis. And the other side, we know what is the input and we know what output is we want, and we want the system that can convert our input into the output. So we want to know what exactly the system should be. So that is what we call synthesis or design. So the whole purpose of studying this subject is, first thing, to understand what signal is, what system is, and then analyze the working of every system for any given signal. That is the analysis. And then we get into the main purpose of doing this is design a system such that it converts the available signal into the signal we wanted. So that's in the first unit. Then in the second unit, we want to have a good understanding about the signal. So to understand signal better, we try to understand the Fourier series and Fourier transform for any given signal. That is, any time signal we have, that can be represented as some of the orthogonal signals, and these orthogonal signals can be simply sinusoidal and cosinusoidals, and these can be used to represent any signal, whatever be the shape of the signal, whatever be the type of the signal. We can represent the signal as sum of sines and cosines, and that is what the aim of Fourier series and the Fourier transform is. And in this we just try to understand what Fourier series means and how that is computed. And so for a given signal, how to compute the Fourier series, and the spectrum, that is what components of the signal we call the spectrum. So the spectrum of the signal can be understood through applying Fourier series and Fourier transform. And the other way, the inverse Fourier series or inverse Fourier transform can be used to convert a spectrum back to the time series or a signal. So this is what we are going to look at in the second unit. And once we are good at understanding the signals, now let us turn our attention towards the system and try to see how to describe a system. So let's start with a simple linear system only, where the expression for any system is linear, mathematically linear with time. So that is a simpler system we are dealing with, and once we are through with a simpler system, then later we can think of applying the same knowledge to nonlinear systems too. So under the linear system, what we try to do is how to represent a linear system. So to represent a linear system, we can make use of some standard input and connect the input and output and try to correlate that if this input is there, this output is there, then this is the system. So for a system, we give an input, a standard form of input, and see what the output is. And if we get a same pair of input outputs, then we can somehow correlate that the two systems we are working with are some way similar to each other. So this similarity we can achieve through using some standard inputs. So one of the standard inputs is the impulse input, and when a train of impulses is applied or an impulse is applied to a system, what comes out of the system is what we analyze. And then every system will have a pair of input output. So the input is an impulse, and the output is what we call a response to the impulse input. So in short, we can say impulse response of a system. So we know that the impulse response of the system is directly correlated with the system itself. Therefore, somehow we try to connect the two ends and say that if system is this, then the impulse response is this. And in future, any time we get a similar impulse response, then we can correlate that we know this system should be similar to the one which has got a similar impulse response. So that's what the aim is, to understand the system. So somehow we need to put a whole thing under a mathematical lens. So create a mathematical world for a system, mathematical world for signal. That's what we are doing in this series. Then we look for different filters like low pass filter, high pass filter, band pass filter, which a system may behave like, because no system can allow infinite bandwidth signal, that is from 0 to infinity on frequencies. It cannot allow. Some frequencies it allows, some frequencies it will not allow, depending on which allows, which is not allowed. We can say that it can allow only low signals, then low frequency signals, then we can call it a low pass filter. We understand that that system allows only high frequency signals, then we can call it a high pass filter. If we know that a band of frequencies only is allowed, then we can call it a band pass filter. Or except that band everything else is allowed, only that band is not allowed, then we can say that band elimination filter and all that. Yeah, to understand all this, how the system is working with a signal to generate the output, there is a fundamental operation to be performed, and that fundamental operation is what we call convolution. Yeah, it's one of the most important activity we have to understand while learning signals and systems. So convolution is an important tool to understand the response of a system for any given signal. So we need to understand the convolution and its properties and all that. Then when we are trying to compare two signals or two systems, so if we are comparing two signals, then we try to see how they are related to one another. So there is something like correlation we have to understand. Or if we are trying to compare two systems, then for a same response, that let's say for a what is the impulse response of system 1, what is impulse response of system 2, try to compare the two responses and then understand whether the two systems are similar or dissimilar. So there we need help of what we call correlation. So all these issues we look in detail with appropriate examples and day-to-day life examples. We just look here and try to understand all these concepts and make it as simple as possible. Then unit 4 we talk about Laplace transform, where Laplace transform is mainly dealing with the system, and system can be represented in terms of its response. So at some time the response of the system can go to 0, and sometime it can go to infinity. So the condition for which the signal system response goes to 0, we can call it a 0, and the situation when the system's response go to infinity, we call it a pole. So we do analyze a given system and then look at what conditions there are zeros and what conditions there are poles. So now we can just start talking about a system more mathematically in terms of zeros and poles, and that is possible only through what we call Laplace transform. So this Laplace transform is basically used for continuous domain signals, but the whole thing, if you convert that into discrete domain, then we do need a different transform which we call Z transform. The same Laplace transform, that is a Laplace plane, that is the S plane we do have. In that S plane, the different positions we do have poles and zeros of the system, and when we talk about the discrete version of the things, then the whole situation changes, and how that situation changes and what actually happens, and how that the Laplace domain is converted into Z domain. All these details we look in this unit, and once we get into this unit, then we start looking at the properties of the Laplace transform, properties of the Fourier transform, properties of the Z transform, so, and then something called region of convergence, then their properties, inverse transforms, all these details we look at that. So this gives some visual details about what signal is, what system is, so we can start visualizing all these things, and we are better able to understand, we have a better ability to understand when the concepts are projected in the form of pictures. So visualizing is much easier than writing in words or writing in mathematical expressions and all that. So better than that will be some picture or some graph. So that's what the various planes talk about. S plane is a Laplace transform visualization, and Z plane is Z transform, Z transform visualization. So we can understand what exactly happens for different systems, and these different systems can be directly visualized through their positions of zeros and poles on that domain, and then we can understand what exactly is happening and all that. So then we get into the unit 5. Unit 5 is current world, where whole world is working in digital domain. but all the inputs available in nature are in analog domain or continuous domain. So there is a need to convert the continuous domain signals to the discrete domain signals, and for doing this, the first process we do is called sampling. So we sample and then convert the continuous domain signals into discrete domain signals. So for doing this, we do have some requirements, and these requirements are clearly stated through what we call sampling theorem. One of the important things in digital communication is the sampling theorem. We just try to understand what sampling theorem is, try to work with analytical and graphical proofs for that. Then look at the impulse and natural flat top sampling, different types of sampling we have. Then there are some issues like aliasing and why do we require reconstructions and all. Then while comparing the signals and all, we do require something called correlation. Here we use cross correlation, that is between two different signals, or auto correlation, that is the same signal is tried to verify whether a part of that is repeated or not, and so that is auto correlation. Then we have to look at the various density relations on the spectrum side, that's energy and power. So a lot of mathematical things are there, but nothing to worry. Let's break all these mathematical equations into our daily life examples and try to understand them as easily as possible. So we just try to make these concepts the easiest possible way. So I sure you enjoy this journey with me in understanding this core concepts of signals and systems. So welcome to this world of signals and systems simplified. Thank you.